All right. I'm ready? Okay. Welcome to day 2. I hope everyone slept well and is ready for another really long day of learning and doing. So this is C++ 2, so it's plus, C++, and hopefully that makes sense to everyone. If not, let's stop now. Okay. So the first thing I want to talk about is this concept that C++ has called const. It's a very confusing syntax because it's this one keyword that can do different things in different contexts. But it's very useful. So we want to make sure that everyone knows how it works, how to use it, and how to read code that uses it, and identify code that might be using it incorrectly. So the purpose of it is code correctness and speed. And it's not speed in the sense that you can optimize things better. It's speed in the sense that if you want to make sure that something isn't changing your data structure, you don't have to copy it and then modify it and then check and make sure that it's the same. You can just enforce that it cannot change. So it allows you to pass things by reference instead of by value and all this other stuff. And what this keyword does is it indicates that something is unmodifiable, and you can apply it to variables, function parameters, return values, instance methods, etc. So in C++, it's equally valid to put the const keyword before or after a type. It means the exact same thing. So the example I have is const int 5 equals 5, and int const 5 gets 5. Those are equivalent in C++. And this means that now this variable called 5 is unmodifiable. If you try and say plus 5, you're going to get a compiler error. So that the compiler actually enforces this. Using consts is preferred to using the pound define for numerical constants, because basically this is a preprocessor directive, and what happens is when you're compiling, it just pops out the code and pastes in this number. So instead of doing that, we want to actually treat this thing like an integer, so we know that it has this type and we can use it that way. In Rosetta, we always put const after the type, so we would prefer the int const 5. So that's a convention that we use, and it makes life a little easier when everyone does that the same way. So please do that, even though this works. It's just a social convention at this point. So now I have lots of examples, and I want you guys to ask questions if it doesn't make sense, and let me know if something's unclear about it in any way. So this is a complete program. You can compile this and run it, all this stuff. So all we're doing is we're defining this global variable 5, and we're adding to it, and then we're going to print it. So we compile, and I use Clang, and we run, and it prints out 6. Okay, so this makes sense to everyone, right? All we've done is add to 5. So now if we make this an int const 5 and have the exact same main function, compile it, we get a compiler error. It says read-only variable is not assignable, and because Clang is awesome, it says, this is the problem. You cannot do this. So this is really, this I hope demonstrates a little bit about why this const concept is important, because you can say, I don't want this to change, and the compiler is going to do that work for you to make sure that it's not changing. So this can become a little confusing with pointers, and we typically don't use raw pointers, but I wanted to go over this a little bit because we do have const owning pointers, and I think it's important to know how those work. So can we let's get a poll of the class and see what everyone thinks each of these does. So let's look at these, and I'm going to ask a little bit. So let's give it like 30 seconds or so to think about it. Don't worry about the J. That's there because in Google Docs, things don't look the same when you present them as they do when you're editing them. It's a great technology. And the wind is blowing. Okay, so does everyone have an idea? What's A? Oh, what is A going to do? Does anyone have any idea?
Is the memory location the same? A list to be added is this? Yeah. That's not change the point to the address. It can always point to the same thing.
So,
the pointer to the constant entry can't change the too. Yeah.
Right, that's right. So the pointer it's a pointer to a const. Okay, so this is the same syntax we saw. So we have this const int, right? What about B? It's identical, right? It's equivalent because we can reverse the constant type. So these are both saying I have a pointer to a constant integer. What about C? Right. So in C, the pointer is constant. The memory itself is constant.
Oh, I thought the first two memory addresses.
No, that's the tricky thing. So that's why I wanted to go over this, because this is kind of confusing. Actually, I have yeah. Okay. So this is the syntax for a const pointer, and you can take it further, and you can have a const pointer to a const value. So you can just start saying const star const, and that's fine.
So that would mean the last one means what the memory location is. Yeah.
You can't change where it's pointing, and you can't change what's in there. So that's like a super constant.
So for that last one, you could not like deallocate it, or like so you couldn't set it to null or something. Would that be changing?
You couldn't set it to null, but if you can go out of scope and you can call delete on it and things like that.
Okay.
But you can't change the value of it.
I think what it means is that would leak memory, right? You couldn't delete it. Or could you?
You can delete it. You can't change it, but it's just a variable like anything else. But you can't say gets null. You can't assign things to it. But typically, if you think you need to do this, stop.
Yeah.
But this is basically what a const owning pointer is. So if you saw when you looked in those type defs yesterday, there's all these things that say COP, and these can be casted from OPs to COPs simultaneously. So if you don't need to change something, you can take a COP as an argument. Yes?
What would be a reasoning? I know I saw them yesterday, but like, what would be a reasoning for using the const with a variable?
Right. So let's say you want to score a pose. And so scoring isn't const on a pose, it's const on the confirmation, which is inside of the pose. But basically, imagine what could happen if, so what const is going to say is that those coordinates can't change, right? So imagine what could happen if a score function could change that, and you had no way of telling for sure that the coordinates hadn't moved. And so let's say you're evaluating 50 score potentials, and on the 13th one, it changes the coordinate. And then after that, everything that gets evaluated is on a different set of coordinates. Yeah. So what the const allows you to do is to know for sure that that's not changing.
Cool. So then, follow-up question, why would you want to make a const pointer?
A const pointer?
Yeah, why would you want to fix an address in memory?
So const pointer works a lot like a reference. That you set it up at the time of creation, and then you can't change it after it's created. So it would prevent you from doing anything stupid like incrementing the pointer and corrupting your stack.
So you couldn't do like that link. You couldn't do like a linked list. Then, right?
Sure. Yeah, you wouldn't be able to do a linked list with const pointers inside the linked lists.
Another application for it could be if you have multiple pointers to a single instance of something. You might not. You might want to guarantee that you're always sharing the instance, as opposed to maybe reassigning it to a different piece of memory. And now these two things you thought were pointing to like the same pose are pointing to two completely different poses. Okay. Is this making sense so far? All right, so now let's talk about function parameter constness. So this is what this looks like. So you can basically say when you talk about your type that this is an int const as opposed to just an int or anything like that. And notice that I'm taking a reference to the integer, and that's kind of, we'll talk about why you want to do it that way in a little bit. These have two major purposes. It's a technically enforced pledge not to change the variable within the function. So what I mean by that is that, again, the compiler will not let you change the value of that variable. And it allows const flavors of variables to be used with a function. So if I have a const int, I can't pass it into a function that doesn't take a const int, because there's no guarantee that it's not being changed within there. Those aren't allowed. So those are the two purposes. If you have something that's const, you can continue to use it. Okay. So, this is the non-const version of that same function. We just remove the const keyword. And I don't know why that slide happened. So this is the reason that it's important, is you don't know if you see something that's non-const and a reference, if it's just going to increment the variable, change it in some way, or if it's not going to. Right, so with this, we're just reading the variable. So you have the same function argument here, but it could be changing it. It might not be. That's kind of confusing. But if you're using const, you can basically say, I'm not changing this. So that's the reason for using that. OK, so now let's look at another example. This, again, is a full C++ program. If you have the slides, you can just copy and paste this into a text file, and it'll run. Or will it? So here we have an integer. I'm just calling it 5 again. And we have this function, returns an int. And it's called maybe I do something crazy, and it takes a reference to an integer. So from the perspective of this main function, all we're doing is we're going to print 5, and then we're going to print the result of maybe I do something crazy, and then we're going to print the variable again. Okay? So let's look at the result of this. So, oh yeah. So think about what the output's going to be. Write it down if you want, and then we can compare that. So I'll give you guys a few seconds to think about that. Feel free to talk to your neighbors about this.
We're wondering where the trick is.
I'm so tricky that there might not be a trick. You'll never know.
This is just that the idea that a function is changing something that it's not returning. It's like a side product of a function, right?
Right. It's kind of the implications of passing by reference.
Yeah.
Is what this is supposed to show.
Yeah, I do this stuff all the time. It's so frustrating. We're like, oh yeah, I forgot to write in my comments. This thing changes to really annoying. Not a good idea.
Right. We'll talk about that a little bit. Okay. So does everyone have an idea what this is going to print out? 506. All right. That sounds good to me. 506. So this function returns 0, so when we print it here, it prints out 0. And then since we incremented a non-const reference, the value of it is changed because we're actually talking about this integer here. And as a side note, these examples have lots of global variables. Don't do that. That's just so it fits on a slide, not as an example of the way to do this. Okay, so now let's mix some const in there. So the only difference here is that now we have an int const 5. So I'll give you guys a few seconds to think about what's going to happen here. And again, feel free to talk to the people around you and get an idea. All right, so does everyone have had enough time to think about what's going on?
We have multiple
We know what is going to happen.
We know what's going to happen, but I haven't whittled it down just yet.
We've enumerated all the possible things that happen.
Okay, well, who wants to say something about you guys in the back?
It's probably going to be a compilation error because we're trying to implement the level of
Great. That's exactly right. So we get this really long error, and it says, no matching function call for maybe I do something crazy. And that might be confusing because you're thinking to yourself, there is a function called this that takes an integer. But it's actually that const int is considered a type. So there's no function that takes a const int. So that's where the error is. It's not when it tries to change it. It's actually when you try to call the function that you're getting the error. So these kinds of things sometimes, when they're littered throughout your output when you're compiling Rosetta, can be really hard to break down. But hopefully you'll think to yourself when you see no matching function call to something that I definitely have, maybe there's a constness issue that you should look into. Okay. We've got more. Okay, so now we have a const here and a const here. So we fixed the problem, right? The problem was there's no const, no function that takes an int const. So we changed that. Now we're going to run again. So what do we think is going to happen if you guys a few more moments?
It will complain again.
Right. Where is it going to complain?
Plus input.
Great.
Is that really like the most logical thing for execution? It's just like not care, like when you try to increment it.
No.
No, because it should just keep it at whatever's value.
Would you?
It doesn't work.
So I think it's tempting to think that way, but imagine what could happen if your program could just at runtime decide not to execute certain lines of code that you told it to. That could be a problem. Instead, it's saying to you in advance, hey, I'm not going to be able to do this, so I'm not going to pretend that I can. It's very honest. So here's the error. It's just a read-only variable is not assignable plus input. So now it's not telling you that int const 5 is the problem. It's telling you that input is the problem. It's in the scope of this function. Okay, those examples kind of highlight the differences between the different types of const between just the variable and the function parameter? Any questions? Great. Because it is kind of confusing, I think, that they're the same, but they kind of do different things. Okay, so now we have a different example where we have, now maybe I do something crazy. is this for loop, and it goes from j is 0 to j is less than or equal to input, and then it increments j, and it prints j. So we still have the same main function, cout 5, cout maybe do something crazy, and then cout 5. So what do you guys think is going to happen in this situation?
0, 1, 2, 3, 4.
It's not printing the 0, 1, 2, 3, 4.
Yeah, this is be 0.
5, 0, 5.
5, 0.
Oh, yeah, there's a 0, you're right. Yeah, that's right.
Looks okay. But you're smiling a little bit.
Looks like there's lots of different theories going around now. Okay, so what's going to happen when we compile this?
It should compile.
Right, it should compile. And what's the output going to look like when we run this?
It's like 5, and then on one line it'll be 0, 1, 2, 3, 4, 5, and then the next line will be 5. Oh, 0. Okay.
Because look, everything can happen.
Okay, so 0, then 5.
Okay, so let's take a look at that. So here's what happens. We compile it, you get no output, it just says hooray. You run it, you get 5, and then from that for loop, we got 0, 1, 2, 3, 4, 5. Then you print the new line, then you print the return value, and then you print the value of the integer, and it's unchanged throughout. So there's the example that finally works. So now you can also have a const return type. So this is another form of const. Again, we like to put it after the type. So the major purpose is really to provide read-only access to some otherwise private data. If you want something to be able to modify that, you should copy it and let them modify it as they feel. But since we're returning a reference, we should make sure that you can't just start changing something's private information out from under it. So that's the goal of this. It's really easy to misuse this kind of const. So imagine if this ampersand's gone. Right, so now I'm returning a copy of the string. Well, who cares what you do with it at that point? So it's really easy to just pop consts on everything, and then when it's not actually improving data integrity in some way. So be aware of that when you're looking at return types.
So you usually see these like in association with private member variables?
Typically with like an accessor. So if you're say you're the minimizer and you have some strategy for minimization that is stored as a string, you wouldn't want me to get a reference to it, modify it somehow.
Yeah, the grain method.
Right, because you can imagine that when you set that up, there could be other setup that happens, and so you want to make sure that you have to go through that pathway to do that.
Okay, so it's not, okay, let's say there's a private member variable 5.
Yeah.
Would you say const? Would you make that const too or not?
So if you want to provide a non-const reference to it, then you should probably think about why it was private in the first place.
Okay.
Right, because if it's private, it means that you want to control that and you're responsible for the integrity of that piece of data. And so that if you're going to break down that barrier, there's something going on with the design of that should be reconsidered. Does that make sense?
Yeah, then I just don't see why all private data isn't constant.
It's only when you're returning it to something else.
Okay.
So if you copied 5, if you copied in it instead of gave a reference to it, you can do whatever you want with it. It's a copy of it. You're not modifying me. Or maybe I want you to give it to you const. There's different. It's going to be more or less appropriate in different situations. So you're going to have to really, but you should know the consequences and the implications of these kinds of return types. And a lot of times they say that qualifier gets casted away or something like that if you just assign it to an int. Okay, so let's take a look at some of this stuff. So here we have some const instance methods. So here's this really great class called myClass. It has a single private data member called s underbar, which is a string, and then it has accessors for it. So this is the const return type that we just talked about. But if you notice, there's also this second const. So we're going to kind of go over what that means. So the major purpose of this const instance methods, which is this const, is to provide read-only access to private data member. So here's an example. Can everyone see this, or is it getting to be too small? As the example sort of got more complex, my solution was to shrink the text. Here's that same class, but now we have a constructor that sets s to foo, which is probably the most creative thing I've done ever. And so now all we're going to do is we're going to make a const, a pointer to a const myClass, and we're going to call that C. Another thing that I've done. So not only do we have global data, we also have single letter variable names. Don't do that. And then I'm going to try to set string from foo to bar. Okay?
Why,
So,
why, can you remind us here, why did you use the arrow there?
oh, this is a pointer.
Yeah, okay.
So you could dereference it and then do the dot, or you can use the
It's just
dash
a
greater than
it's
arrow.
It's just a dereference.
Yeah, it dereferences and calls methods that
Okay.
way. Okay, so we're going to compile this and run it. Talk amongst yourselves, and let's get an idea of what's going to happen here. Talk.
But that's fine. Right, you're not modifying.
Right, but bar is not
It's not a variable, though, by definition. It's constant.
Oh, is that true?
I don't know. I would think.
If you don't declare the string to be a variable, is it const or?
Well, I guess that's the mystery, isn't it?
Is it?
You don't declare it as a variable.
And double mystery.
Mystery inside of the string.
It's in the conception.
It's an inception. Yeah, I would. Seems like it's. Although I don't know if that's the right answer.
This just shows I don't sound.
Oh, that'll change.
Isn't that just a constant? It's just a constant can you have yeah, because set.
Sure.
Okay, yeah, you can't change it. Yeah,
You will get there.
yeah, you will.
That's how you.
You think so?
Yeah, I think so.
lead our answers? Oh,
That would be fun. I didn't thought of that.
I think that's a reasonable thing.
I should have made you guys buy me burritos.
Oh, so they're like M&Ms or something.
M&Ms.
I don't mind.
Okay. So it looks like most people have sort of come to a conclusion.
Merge it.
What do you guys think is going to happen here?
I think we'll get an error.
A compiler error, you saying?
I think so.
Okay. Where?
Wouldn't it be when you're trying to pass? Well, yeah, maybe it won't be compiler error. But the problem is when you're going to pass bar, right? The set string method.
So you're saying that passing bar is the problem.
I think it's because it's not constant, so.
Bar isn't const. Okay.
Wait,
So there's
No, well, the class.
the problem is
Yeah.
invoking set string.
Your question is
Yeah.
so say it again, Kale.
You can't invoke set string because set string is not a const method, and C is a const object. You can't invoke non-const methods to const object.
Exactly. So what does it mean for a class to be const? It means that these data members can't change, and it means that you can only call const methods. And const methods can't change any of the data members. If a class is const, the data members can't change, and you can only invoke methods that are marked const.
But hypothetically, if it wasn't a constant pointer, could you do the next line?
This?
Yeah. Yeah.
Yes.
Yeah. Okay. That's fine.
So what happens when you do this is that you're basically casting it to a const type. So you're just saying that within this function, I can't change that. So it takes a reference. So you're guaranteeing that the string s is the same when it comes out as it was when it came in.
It's actually just slightly more complicated than that, where what happens is the enclosed in quotes there, the bar, is a seat-style string. And that has to get passed into the constructor to a standard string. And it constructs a standard string and then treats it as const for the duration of that set string function. And then at the end of that function, it destroys that string. So you can do funny things where you pass in objects by constant reference. So if you have a function that takes a float constant reference and you have an int, you can pass that int in and it constructs a float and then at the end destroys that float. But if you have a function that takes a float reference and you pass an int, it'll complain. It'll say, this int is not a float, I can't pass between the two. So there's some funny stuff that goes on with Const references in the background that makes things like this just a little bit more complicated. Fascinating.
But it would work. Okay, so let me try to compile it. And you get the set string, not viable. This has type const my class, but function is not marked const. I will say that I recommend using Clang because you get error messages like this. I think that if you've been exposed to what const means, this is very clear, as opposed to what you'd get out of something like GCC. So hopefully this makes sense, and you guys were able to figure out what that was just by looking at the code, so that's great. So now what if we, what are we doing here? Right, so the point is that this was lacking a const right there. And that's really the issue that we have. So we could call getString. Bless you. Okay, so what are the restrictions that are imposed by marking a function const? Like we have right here. Non-const methods cannot be called from const methods. So if you have a set of const methods, you can only call the other const ones. The class data members are const within those methods, so you can't modify them at all. And if a member is an object, you can only call that member's const methods. Was that too many levels? Clear? So basically, just like if you have a member that's a class, it's const, which means you can only call the const functions on it. So that's what happens if you're in a const function. So here I have and part of an interface from a real class in Rosetta. And I have removed all of the consts. And it might be a little bit confusing because the comments leave something to be desired. But what I'd like you guys to do now is, with people that you're sitting with, go through this and think about where the consts should go. And then we're going to put up the right answer, and we're going to talk about each const. Okay? You should get a partner.
What are we looking like?
Okay.
I'm confused.
Wait, don't we know what the functions are supposed to do in the first place? Like defunct, who knows? Like who knows?
All right. Defunct is it computes the derivatives from the variables, and it takes variables and derivatives. We'll go over it, and there's not really going to be wrong answers or grades or anything like that. It's just a thought exercise to where you can say, this is the consequence of putting a const here, and we're going to go over that.
So like when you're using const,
Mm-hmm.
you're looking just for
Yeah, they changed the
times when you're putting in a variable. You don't want, you'll get something from having a specific variable, but you don't want to.
Right. It's basically a read-only form of that variable. So there are situations where you can say to yourself, if this could change, it would. I'd have to do extra work to make sure that it wasn't. I think the coordinates of a pose when you're scoring is a good example of that, right? So imagine like this moves, and all of a sudden, well, these things that I computed in the beginning are irrelevant now because I changed it, and I can't tell where it's happening. But you can say, no, you can only read them, and then you can calculate something based on that result, and you are guaranteed that it's read-only. Does that help at all?
So so somewhere you're calculating something from a variable, and if it changed, it would be really bad. You don't
Right.
also need
Or
it to change.
in the example of the set string, right? So that was const in the function parameter, right? So that means that if I say set string to bar, it would be really bad if you could set it to something other than bar in that function.
What the
So in the previous example, we had a class where it had a string, and there was a function called set string, right? So I was setting that s under bar to some string. But if I could say set string to bar, and it set string to Brian, that would be bad. Right? So you can say, no, this can't change this in this function. And so you can kind of guarantee that.
Oh, okay.
And also it was passing it by reference. So if I changed it in that function, it would change it outside of the function too. So it's about thinking about where the data integrity is really important. And you can call const functions from non-const functions. So if there's like a part of it that you say this needs to be the same within this section, you can roll that off to a different function if you need to. Yeah.
Effectively, anything that's taking a reference from like another object or something, you don't want to be changing any of the values.
Unless you do.
Yeah, but this is just.
Well, actually,
You said this is calculating the derivative, right?
Right.
Well, wouldn't calculating the derivative not affect the original value?
Of the variables or of the derivatives?
Of the variables.
can't change
Yeah.
any.
Right.
Yeah.
So we want to think about what happens if you change a non-const reference versus what happens if you try and change a const reference and what that would mean. So you can mix and match. You could do some things some other ways. What would happen if you pass in a pointer and then assign it in a function? That kind of thing.
No. I'm just saying that if you I guess you need to know more exactly what this does, but I'm just saying if you were trying to calculate the derivative of some variables, like you wouldn't want, like, I guess it matters what method. I mean, the method I know to calculate the derivative, you don't need to actually change the original value, the original variable.
Right.
Yeah, you just.
Exactly.
Yeah.
Right. So you probably
yeah, and especially if they're like energy terms or something, you definitely
Right.
don't want to touch them.
exactly, because some other function somewhere else is
Exactly.
responsible for determining that value.
Yeah.
Exactly. So that's the thing, is it's a the separation of responsibilities.
Exactly. Yeah.
Great. Sounds like you're getting it. You good?
Vaguely.
Okay.
So the second function gives you the derivative, or it returns you the derivative by reference. I mean, it's impossible to.
But you know it has to use that.
Sorry?
The second function.
What about it?
It takes the vectors and the derivative of of those, or it returns the derivatives by reference.
It returns a void. So
No, by reference.
everything gets returned by reference, right? So it still exists after the fact.
I'm talking about the result. Is it returning the result by reference or not?
It's
So
it's a
Is an
void.
input a constant input, or is a return label?
It computes the derivatives. I'll say that it computes the derivatives.
It computes the derivative.
Right.
So it returns the derivative on D.
I wouldn't call that returning.
It just says it can't change anything about.
It's
Return by reference, right? That's the name.
well, it's void. It doesn't return anything.
No, I'm not talking about the return value of the function. I'm talking about return results. The results by reference.
Yes.
Right, but I mean, you get that back anyway, no matter what. If you pass in by reference, it's still there when you're done the function.
Yeah, but
So I just wouldn't call that. It's a syntax thing. Like I just wouldn't call that.
okay.
I just wouldn't call that returning.
Yeah, I'm just asking because I would like to know if that becomes or not.
Right, it's computing those derivatives.
Okay.
So
Okay,
that's
that makes sense. Thanks. That might actually be the
sure. I'm trying to get out of the way of the camera.
Just to be clear, can you explain to us again what a const method?
A const method.
Yeah.
A const
Is allowed to
method.
do? What is it allowed to do?
It can read the data, and that's it. So it can call other const methods, and so if you have const data members that are classes, you can also call their const methods.
Okay.
But beyond that, you can't really do very much.
Here's more.
It can do calculations. It can
Oh, yeah.
It can declare variables.
I'm talking in terms of access to information.
Right.
That's how I'm thinking of it.
Variables declared on the stack.
So can it take non-const references and modify them as arguments?
Yeah, as long as they're not data members.
That makes sense. So,
It
I mean, here's
if
what we're
it- if
confused
it calls
about.
some other function that takes like a non-const reference, then it can't give one of its private data members as an
Right.
argument to that
Right.
function.
So we're talking about the defunct.
The defunct.
And so we've sort of deduced that the vars could be const, but that DE vars shouldn't be, assuming that it's taking vars and using that to calculate DE vars and fill it in. But now we're trying to decide whether or not defunct could be a const method, or if it is not a const
Yeah.
method.
And so I think what you really want to just think about, more about the consequences of what that would mean, more than about getting it absolutely right. Because again, without knowing exactly what this function is, it's going to be pretty hard to know for sure. But we want to be able to have a conversation about each const that is there and what that means and why it's there. So it's okay to not come to a concrete conclusion, just to know if it's like this, then this is the consequence. If it's like that, that's the consequence. Yeah.
How do you can you switch a variable type between like a const and non-const?
You can turn something from a non-const into a const.
So,
Just by passing it into a function that takes a const. It'll just
so
treat it
before
as
you had
const.
The example where you had a const that the variable took in a non-const and that gave an error. But if
Right.
it were the opposite,
That would
if
be
it was
fine.
just an integer outside and the function
Right.
took in a const integer, it would just within that function it would be a const.
Exactly. It's a scoping.
Okay.
situation. Right, that makes sense, right? You can always say, I can only read, but you can't say, well, this started off as I can only read, but now I'm going to be able to write too.
Yeah.
Ooh. Okay. Sure.
A pointer that points to something that has a constant value, and then you have a function that you're going to pass that to, but you pass just the address. Is there any way to enforce that constantness?
You pass just the address of the pointer?
Yeah. Does it have any way, the compiler have any way of knowing that it must enforce that?
It would depend on what does the function take?
So yeah,
What is the type of the function?
Pointer. It just takes an address. So I guess.
I don't know how. I don't know about. You'd have to have a type in a function in C++.
So the type it would be.
Like if you cast the address to an unsigned int or something, or yeah, something like that. Is that what you mean? And then you like convert it back to hex and try to read out of it.
Yeah. So you have. Yeah, you have to do some strings.
Yeah, you have to try really hard to make that happen. Is the real point. But typically, you're using the types in your functions to make sure that you can't do something like that. I was trying to figure out how can you do that. You'd have to go. There are ways to cast away constness. It's called a const cast, and those are done in really specific circumstances. And if you think you need to use it, you probably don't. So that's why we didn't really talk about it too much. But there is kind of a mechanism for this, I imagine it uses sort of that same idea where you take the address, cast to an int, pass it around, cast it back, and so you can sidestep it that way.
I don't know. It seems like.
But it's not a good idea.
Pointer, it would be enforced, but it seems like there would be a not completely awkward scenario where this is.
So typically when people want to cast away constness, it's because they're using some third-party library and it returns something that's constant. They want to modify it, and they know exactly what they're doing. We shouldn't be in the situation within Rosetta because we write the libraries. Does that make sense? Okay.
If the signature of a function, it's like the signature is a reference. But what you're passing is actually here to you as a pointer. It seems like this almost sets up the situation. Yeah, never mind.
Okay. We can talk more about it later if you want. Okay. Has everyone had time to think about every place you could put a const and what that would mean and why you might want to do that?
Oh, that's cool. Source tree just lets straight into
Okay, so I'm going to put up the constified version of this, and we're going to go through what it is. And if people were confused, didn't meet their expectations, let's talk about that. Come on. Okay. So now we got a bunch of consts. So let's talk about what's going on here. First up, who thought this was going to be const this way, with the const parameter and as a const function?
think there'd be a const outside
Okay.
Yeah.
Yeah. Sure.
Are those all the constants that you need to put there, or just all the constants that the person that writes this thing put there?
This is as it exists in Rosetta.
No, I understand that. The question is, do you need all those constants or not?
I'm sorry?
Do you need all those constants or not?
Do I need them?
Yeah, because that's the question, right? That's most that we can get. Like, we can compile the program with which constants there.
You want all the constants.
You want all the constants. Okay.
It's a matter of data integrity. Right? So what this says right here is when you use this operator, the state of this class is unchanged. So you want to note that. Like, hey, I'm not changing this. So that if you do have a const copy of this class, you can still use this. So if you didn't have this and you had a const version of this class, this function won't work, this function wouldn't work, this function wouldn't work. So you want to note things that are const because it allows you to use it in different situations where you don't want it to be modified. Does that make sense?
It makes sense, but if I don't know what the program is doing, it's difficult to know.
Oh yeah, this was...
It actually communicates more than having it not const, right? It tells you a little bit about the state of the code that it gives in its interface. I'm not changing if you call this function. And similarly, when you pass in this multi-back, you're saying, you're pledging that this function isn't going to change the contents of that multi-back.
Right, so I think something like this function signature here really tells you a lot about what this does, even without looking at it. It says, this is const, this isn't, and it doesn't change the state of the class. So what that says to me is that we're going to be changing this. We will definitely be changing this.
I just want to make sure.
Yeah.
So, say I've created this class with all these const functions,
Mm-hmm.
and then I created an instance which is not const,
Mm-hmm.
of this class. So I can still call those, obviously I can call everything in this class, and I can change the object even though the function is declared const, or all those functions that are declared const can't do anything to the object.
Right. So these functions cannot change the state of the object. So that means the data members.
The object created a non-const instance.
Right. So within the scope of this function, all the data members are treated as const.
Mm-hmm. All right.
So you can't change them within that function.
All right.
And you can't call functions that can change them.
Right, right. And if I created a non, but if I created a const instance of that object, I can only call functions that are const within the definition of the class.
Right. So if you have a const class, you can only call the const methods.
All right.
But if you have a non-const, you can do whatever you want.
All right.
Yes.
In the second function, the second set of variables do not have a const
Right.
beside them. So since the function is void, it might change them internally, but it will not return a changed set of derivatives. Is that right?
Yes and no. So imagine what happens when you pass in a pointer, right? Because we're passing this by reference, the ampersand. So that means that I have access to the actual memory that this variable is declared in, right? So that is containing that variable. So if I change it, and then outside of that function, I look at it, it's going to be different than when it went into the function. So even though I'm not returning it, I'm still changing it.
So then when you have a const at the end, what does that mean in the context of the second set of variables?
Great. So that's a really good question. So this const means that the data members of this class aren't being changed. So
the vars and vars are not members of the class.
exactly. So I couldn't call this class if I couldn't call this method if vars and dvars were data members. It wouldn't work because it says this needs to be const within this function.
What are the data members of the class?
Somewhere down here. They don't fit on a screen. So
just putting const, say one more. Can you say one more?
what this constant means? So this constant means that within this function, the data members are treated as const. So that means members of the class. So these, so at least this cannot be a member of the class if you're calling it. Does that make sense? So this is going to be called from things that come from other places. Okay. So this was the tricky one and was the reason that this was selected. But basically, we're saying that we're going to calculate a derivative. We don't want to change the thing we're computing the derivative of, because that would be scary. But we're going to pass in something that we're going to populate. So you can imagine that you pre-allocate a vector in some situation, and then you just load it up. And, something like that. So this, the consts in this really communicate a lot of information. So I think that's the other really nice thing about this concept in C++. Okay, and then of course, error state reached. We don't want to change anything if we're going to try to write something out to say, here's what went wrong. Imagine a situation where something goes wrong and you say, I'd like to know what happened, and then it starts changing everything. That would be a big problem. And then this kind of told you, right? So yeah, you can. These things are just not changing the state, but they're for internal use only because they're protected methods. So it's again because they're protected. It's this makes this more okay to return non-const because you can only use it within the class. You're not just going to hand it out to someone else and say, do whatever you want with this thing. So does this make sense? The consequences of all these consts are clear.
Just in that very specific example, returning a non-const post reference inside a const function, that ordinarily would be illegal. Let's say that pose is a data member of the class. So the reason that that's legal, and maybe you're about to get to this, is because the pose inside the internal pose that this class keeps is actually declared as immutable.
I wasn't going to go there. I was going to leave mutable right out. We can talk about mutable if people are interested. Typically use it to have const accessors with things that are lazily instantiated. But we can talk about that later if you care. I can show you some examples in the code. Okay, so hopefully this is clear, especially this one. I think this is probably the most interesting function on this in terms of constness.
So we can infer from
What?
the pose function.
This one?
Yeah, if it returns a non-const and the function is declared const, I can infer from this that pose is not a member of this class.
Or it's marked mutable.
Or it's marked mutable. I thought the whole point of this thing was that.
But let's say it's not marked mutable. Then yeah, this is someone else's pose. Imagine like a mover, where you pass the pose in through apply. You can return non-const poses from other sub-functions that are modifying it. Right, but you might want to make those things protected so that you can only do that within the class itself. But if you see something like this and it's not protected or private, be afraid. It's not a good idea. Okay, so now so that's all I wanted to say about constness. It's really important. It communicates a lot about your code. It helps you prevent mistakes. So it's important.
I would ask one more question. The pose up pose, is the const at the end of that line the same as the const? Same conceptually as the const in the public?
This one?
Yeah.
Yes. It's saying that it's not changing the state of the class itself.
Okay, I'm getting confused because those are all consts at the end of the method.
This is too.
So pose is, okay.
This is a function, see the parenthesis.
So pose is returning a reference to a pose.
Yeah.
Object, okay.
Yeah. So this is the return type is a pose reference. The function's called pose, and it's const.
Okay, so the return, what you're returning, the pose reference you're returning is not const.
Right, but saying that the data members of this are not being modified when you call this function.
Okay, so it's like you're grabbing the coordinates or something like that.
Or it's not a data member. Or it has a couple of strings that say my pose's name is Abba. It's not going to change that to Kevin.
One general question about maintaining long-term codes. Do you put in const when you are absolutely sure you do not want to change it, or do you put in typically when you are absolutely sure this is not going to be a variable, but you're not sure you want to keep it constant? Like, yeah, once you put in a const, you know you're never going to change it. But so, how stringent it is, and what is the general?
Right. So the question is sort of about code design.
Yeah.
We're having a lot of background.
Sure. So the question is, when do you decide to mark a function or a variable or something else as const? Is it an early design decision, or does it kind of happen as you have more developed code and say, oh, I'm not changing this, let's mark this as const? I would say it should be an early design decision. When you think about this, to use as many vague words as possible, this does that, is typically what you're going to be thinking about when you write a function, right? So this is going to take this and it's going to do this with it. And you should know kind of up front what that entails. And if you are writing code and you kind of say, I have no idea if this is going to be changing the input to this function, it's a very adventurous way to develop code, to say the least. But I think that what you want to be doing is thinking about the responsibility of a particular function. So in the simple case, like an accessor, you want to say, someone wants to know the value of this data member. I probably shouldn't change it halfway through the function. So you want to mark that function as const. Or if I have a const copy of this, I should still be able to do that. As opposed to something like, so set deriv check result. Well, this is going to be storing something in the class. I'm setting it, right? This is obviously something that cannot be marked const. So it's a very early decision that's being made. I think when you're thinking about writing a class, you should think about designing an interface and then implementing it. Does that answer the question? Great. Any more questions about const? We can talk about it afterwards too, because it's really a big concept.
I have a quick Rosetta related question. So the pose is not constant, but shouldn't the score function not be constant either, because it should change with it? Or does the score function only contain generally the scores, which are their weights, but not the actual scores of the pose?
Right. So it's going to require a little bit more detail on what these things do. So basically, this class has lots of other classes that are derived from it. And so we have these protected accessors because we don't have protected data in Rosetta. We think that those are bad things. Right? So if something is protected, it means that when you inherit from it, it's treated as private in your context, right? So you still can't call it from the outside, but you can call those things. Whereas things that are private, when you inherit from them, you can't access them at all. So what these methods are doing are giving you access to these pieces of data for this bigger class. And they're read-only because you should be using some other mutator to change those things from the outside, because there might be rules about how you set them up. So they're const because we don't want you to change them. So basically we're saying that this class is fully responsible for the data integrity of its members. And so for that reason, these things are going to be const references, because you don't want to be able to do it behind the scenes. You want to have to go through the correct framework to do that. And like Andrew said, this is marked mutable, so ignore the man behind the curtain on that. Does that make sense? Okay. Good on const? Okay. So we're going to change gears a little bit and talk about function signatures. And a function signature is how a function is identified. It contains the function's name, the arguments, the types, the const status of each argument, and the const status of the function. And if it's a method, it includes the class name. And for virtual functions, which we saw yesterday and talked about for a bit, remember in mover, you had to implement, there are two pure virtual methods, get name and apply. For those to work, the signatures must match exactly. Okay. So can you see this? All right, I will read it. So we have a return type of int, something called awesome function. It takes an int and it returns plus that int. Then we have something that's a double. It's called awesome function, and it takes a double and it returns the input plus 1000.5. So it's a double. So then we're just going to set my int to 1 and my double to 1.0. And then we have some print statements to print out int, my int, after func, run awesome function, my int. And then we have double, my double, after function, my awesome function, my double. Okay? So what do we think is going to happen when we build this?
So it'll be 1, right? The first one will be 1 and 2. Right?
So we have, it's going to say int 1 after func 2.
I think so.
Okay.
I don't see any reason why.
That's people thinking. So I'm just
The
going to.
incremental operator working in double. That can work.
Yeah.
Oh, again,
Oh, yeah.
I mean, it should be fine because they're unique from each other because one accepts a double and the other one accepts an int.
Exactly. So this is the output. Int 1 after func 2, double 1 after func, 1000, 1 plus 5. And again, this was just 2 lines, but you know,
Yeah.
Google Docs. So why does this work? These things are named exactly the same, and it's because they take different types of their function signatures are different. So as far as C++ is concerned, they are different functions, even though to the human eye, awesome function is the same name. Okay, so what if I say, oh, you know, I can do this even easier. I don't need to have that double. So now I have awesome function takes an int and returns plus plus and returns an int. Awesome function also takes an int, casts it to a double, and then adds 1000 plus 5, and it returns a double.
That's not going to work.
So we get an error, right?
We're going to get there.
Well, you have the integrable
You can cast anything, however you want.
When the awesome function gets the integer, it doesn't know whether to output an int or a double.
Exactly. So when you do this, you get an error, and it says return type cannot be overloaded. So what's happening here is that the return type is not part of the function signature. You can change it all you want, but it doesn't make it a different function. You have to change something else about it.
Where do you go between C++? Which compiler do you use to get these more helpful?
Yeah, it's built. We have support for it in Scotland, so we can show you how to set that up if you guys need. But yeah, right. It's pointing right out where the problem is. Okay, so let's talk about overloading functions. So we just did it in that first example with awesome function. It had the same name but a different function signature. So that's called overloading, and it's convenient when you have a really great name. But you want kind of different versions. So if I give you a double, do something different than if I give you an int. Do something different still if I give you a pose. So it can be useful when you can't change the name of a function, and we're going to be talking about that later, not in this talk. So let's talk about overloading constructors. So we have a bunch of different constructors, and we all wrote constructors yesterday, right? When we did the mover. Okay, so there's the default constructor. It's got no arguments. A copy constructor, if you don't write one, the compiler will make one for you. But typically, you don't want this to happen because you're smarter than the compiler. So this is going to call the copy constructor on each data member. So if you have a pointer, it's just going to make a new pointer that points to the same thing and not copy the contents of the pointer. So that's the danger of allowing the compiler to generate the copy constructor. But these are overloaded functions. This has the argument of an instance of a class. And other constructors can be defined to take whatever they want. So you can say, you need to give me these data. I think Matt provided an example with thread yesterday having a few properties passed in at the beginning. And so that would be an overloaded constructor. Really useful. So here's a couple of examples. So I can say my default constructor is just going to set s to foo. My copy constructor just copies the right-hand side string to the left-hand side. And then I have a third one still where I take in a string as a constant reference, and I just assign it within the function itself. So I can say, instead of having to say, make a class, and now set, I can do that in one go. Just say, my class bar. So that certainly can allow you to simplify some things.
So you're overloading the constructor.
Right. Does that make sense how this would work and would save some steps?
Okay, so the default constructor is this first one, right?
This empty one right here, no parameters. And so it's clear how each of these has a different signature. Okay. So now I'm going to talk about static functions. Static functions do not require an instance of a class in order to be invoked. I think of them as a method on the class as opposed to a method on an instance of the class. So that takes, I think, a little bit to think about, but it starts to make sense after that. They do not have access to non-static member data of the class because, again, there's only one of these functions, and you can have many, many instances. It doesn't know which instance you're trying to call or trying to talk about. But they are part of the class, so they can call private methods of the class.
Because we've only really talked about private, protected, public member data in a class. Now where did non-static?
Oh, static. So all those things are non-static.
All those things are non-static.
It's a separate concept, really.
Okay.
Static basically means there's one of it, one thing. So if you have a static method, it's you don't need an instance to call. You just kind of say class name : method.
Right.
So it's
like the math function.
Right. Or do you remember when you made a job distributor and you just said get instance? Right. So that was a static function that sets it up for you. And we're going to talk about that in a little bit.
Okay.
Hopefully it'll become clearer in a few moments. An important thing is that we want to avoid non-const static data. And the reason for that is if you're saying that this is kind of part of the class and it's non-const, that means that sort of what makes that class can change throughout a simulation, and that's weird. So we don't want to do that. Things that are okay to be const static data, you can think of like a map. That might be okay to use as static data. Yeah. So the problem with that, again, is also that they're not thread safe, so we don't want to use those things.
So can you back to that one? They are not thread safe.
Yeah.
Thread is constant static class, right?
Thread, like multi-threading,
Oh, okay.
that kind of thread safe.
Can you use an example of one on the previous slide?
What? Which previous slide?
Oh, no, one forward. Yeah. No, 2 slides forward. I'm sorry.
Forward.
Well, one more. Yeah. I really don't understand the second bullet. Can you give me an example of what you
I'm going to give you an example right now.
Perfect.
Briefly, that has some static data and some non-static data, and we only know the structure.
Do is explain what a singleton is, and then show a singleton. So that'll do that. But first, I want to make clear what's going to be going on in that class, so it makes sense.
What is the singleton?
I'm glad you asked. Sometimes you'd like to make sure there's only one instance of an object, and it's impossible to make a second one. The job distributor is a good example of this. You wouldn't want to have a whole bunch of different job distributors spawning in a single simulation, just the one. Same with factories. You wouldn't want to say, which factory do I go to? You want there to be one factory to get a mover out of, for example. So these things are actually pretty straightforward to make. They have a private constructor, so that means you can't call it. And they have a static private pointer instance as part of the class. So I'll show you what that looks like and what that means. We'll go through some examples. And then they have a static getInstance method. Okay. So that's basically the 3 requirements to make something a singleton. Can you see this? This is like the world's quickest singleton. So here's the static method. It's just got this static keyword in front of it. And it's public. And it returns a pointer to an instance of singleton. And it's called getInstance. And then if instance doesn't exist, we're going to create a new one. Now remember, because this static function is part of the class, it can call private methods, including the constructor. Seeing puzzled looks.
So does the compiler not build a public constructor then? Because you declare it in private?
Exactly.
Okay.
Is that clear? Okay, so, and then we have the same get string, set string. Here's our private constructor. It's just going to make the string foo. We have this private string. And then I like to separate these things out a bit. So I put another private block. And I have static singleton pointer called instance. So there's one of these things. And then you have to initialize it to 0. So that's a null pointer. Okay? Getting looks of disbelief. So let's keep going. So now imagine that code's on top of this code. So here's our main function. And I say, let's give a pointer to a singleton. It's called s. And we're just going to call singleton : get instance. That's that static method, right? So we can call that without an instance. It's going to take that and say, oh, your instance is 0. Let's make a new one and return that.
Can you go back to the previous slide and just have static is fine.
Yeah.
All right, so yeah.
So
Yes.
static, static. Okay?
Wait.
What?
Instance function? At the bottom.
This? Oh, this is initial. This is a pointer. So I'm initializing it to 0. Okay. So here's what happens. We get the instance. We call it s. And we say string val is s get string. And then we set the string on s to bar. And then we're going to keep going. And we're going to say, oh, I want another singleton. So we have this one called r. And then I'm going to print the value of the string in r. So does everyone have an idea of what might happen when we do this?
It's going to fail, but I'm not sure if it's a collision error or a runtime error, because you can't create 2 instances of the same thing.
Okay, so we have hypothesis 1. What else do we have?
Well, 'cause it's just pointing to the same instance. There's not 2 instances. It's just pointing to the same one. But I'm still not sure what will happen when you set it.
So let's talk to our neighbors for a little bit and come up with some
But can you
more.
go back to the code for a second?
Yeah.
Should probably just open this and
You can just say forward and back, and I'll just.
go back. Oh yeah, no, it'll be fine.
And then just alternate between them.
Wait, is this lecture 3?
I don't even know.
Yes.
It's the ++C++.
Yeah, but it's not labeled like that.
So singletons have static and non-static data. Is that what you're?
Mm-hmm.
Is that vaguely correct? I don't. Okay, I don't see why that's an
When
important feature.
we come back, we'll talk more about it.
We'll talk more about it.
Yeah.
I think it makes some sense.
Okay.
You want like some centralized location, like almost like a state or something, and you want everything to access the state. So like suppose you had some like hypothetical. I mean, I don't think this is how they do it. Like they have like one code that every single function needed access to. And you could have it in a single one.
So the
And it'd
code
be like, oh,
not from outside of the class.
Right. I just don't.
I think it's just a way of sharing.
Right, because it's private, so you.
So the same, sure, so
Without creating new objects.
revising my answer. So the same thing, so you can't create another object directly, but you can create a new pointer.
It should
Right.
just specify that there always going to be one. Yeah. So you can't
Okay.
create these instances.
So I hear a lull in the volume. So so what's gonna be the output of this program? Is it going to compile? Okay. Yes. And what's the output going to look like? Right. It's like foobar, right? That's what I heard. Okay. So that's exactly what we get. Initial string val foo, final string val of r bar. So what this was demonstrating was that this is a shared instance of this singleton object. You can make as many pointers to it as you want, but it's the same instance in the memory. You can't have more than one of them. And the only way to get a new pointer is to call this get instance or copy the pointer. Does that make sense? Was that sufficiently staticky enough for you? Good. So there was a question about how these things are actually useful. Can we think of a couple of examples of why you might only want one thing? Aside from a job distributor, factory, score function factory.
Well, I was just thinking it's a great way to have access to some data or some function that you know is not going to change. So I was just thinking of a hypothetical thing where you only had like one pose or something that you were never ever going to change, and you wanted every function to be able to get to it somehow. Then you could just call instance of that single. I'm not saying this is a good idea. I'm just saying you could call instance to that a singleton that had that pose, and you could get it when you wanted it.
Right. So it's a good way of making shared things, and that you want to make sure that it's the same object, no matter who's talking to it.
One thing I will say is global data is something that's best used in sort of extreme moderation. Like, it can be really tempting to be like, oh man, singletons, I'll just put everything in a singleton, and then I'll just pass things back and forth between singletons, and then I'll never have to worry again, and that gets really, really messy. So if you think you need a singleton, and for something that's like new that you're writing, frequently you don't. So
Isn't this just kind of like global data? But
it is global data.
Describe the question with global data. Yeah. So it's like there are only certain circumstances where you ever want global data. If you can think of any scenario where you'd want, say, 2 values for an object, it should not be global data. Like if you want to run a protocol, and you're thinking, for instance, you were talking about this pose that you might want, and no one's going to change that pose. You might be tempted to think, the native pose is the one that I want. And that's great if you have one native pose, or if there were only one protein in the universe, it's one structure. But if there were, say, multiple proteins, thousands of them, you wouldn't want one native pose.
I wasn't saying it was a good idea.
No, I'm just like flushing the example.
But what if it's like if you're doing like MPI or something and you want each core to get the same native, right?
there are ways of doing that without.
Yeah, it's still, you don't want, so with MPI, for instance, you can imagine wanting to have say you're trying to do ab initio structure prediction or something, right? And you want to see how well you're doing, right? That's great if you only want to predict one structure at a time, but usually you want to predict lots of different structures, and so you want a different native for each of those structures. In which case, global data is it's a big constraint on what you're able to compute, or how you're able to run the computations.
Is there any important part inside of Rosetta that is static?
There are lots of singletons, and they're all designed with this idea of like, I've got one huge piece of data that I want to load into memory once, or maybe I want to initialize it just as needed. Or there's a further thing, which is that singletons resolve this load time catastrophe, or global data initialization catastrophes that people talk about from time to time. So for instance, it takes a while to read in the Dunbrack libraries from memory. It takes a while to create And so we have ways of creating them, and then they don't change with the duration of the program.
So these singletons can be changed, right?
Yeah. They're not immutable. They're not necessarily const. There's just one of them. But they're global because you can just, no matter where you are, you can grab an instance to it. So the pointer is the global part. Okay. So I think that brings us to the end of what we were going to talk about in this lecture. Some people had more questions about constness or singletons or anything like that. We're happy to talk about it later on in the day. So, thank you.